Close. Okay, so today's topic then is something called a permutation. And before I get into the official definition of a permutation, let's just do another question, just like we did in our journals. So let's say that there's this ballot here, and you're being asked to go make some votes. My question is, how many ways can you fill out the ballot if? And then here's a couple of restrictions, so we'll just do them one at a time. Let's say that you have to vote for all 5 positions. So hypothetically, you want to vote for president. How many choices do you have to vote for president?
5.
I guess 5. Now, I guess I gotta assume something. If you vote for somebody for president, you can't vote for them again for vice president, right? Doesn't that seem logical? So then you'd have 4 choices for vice president. So like hypothetically, you vote Peter for president, Erica for vice president, Sung Hai, if I'm saying that right, for treasurer, secretary, you do Bill, and then poor Holly, I guess she has to be the social convener. You'd do 5 times 4 times 3 times 2 times 1. Good, that's actually the first thing I want to start with. Yesterday we talked about the idea that this comes up so often, there's a special notation of 5 exclamation mark, which means you're so excited about math that you want to put an exclamation mark.
Jokes.
No. No. It's Friday afternoon. Okay, does that make sense though, that first question? Okay, let's put a twist on it then. Let's say that for some reason, this is like maybe you're in the States, you're voting for president, and you really don't want to make a vote for Donald Trump because, maybe you're so opposed, right? And so you're going to abstain. You don't want to vote for social convener because that's your political protest. I don't know. Does that make sense? Could you do that? Sure, why not? Let's see how that would work out. So you're going to make a vote for president. Actually, let's even do it this way. Let's just pretend that social convener is not even on the ballot. Let's just scratch it out. Not going to vote for someone. How many votes could I have for president then? Still 5, I guess, right? And then 4 for president and vice president, and 3 for treasurer and 2 for secretary. And I guess in this case here, if you were to cross off like some names like I was doing there, I guess it just means that you're not writing down Holly's name. So what's this answer? Well, it's 5 times 4 times 3 times 2. Actually, by the way, it's actually the exact same thing in terms of how many ways there are, because I guess by default, the last person, if you had to put a name down, it would have been Holly's name anyways. But that's kind of a twist where you could have 5 names on the ballot and you could maybe just choose to abstain. That's an option. How about this? What if I were to ask you to vote for only president and vice president? So again, like you really don't care who's treasurer, secretary, social convener. So again, let's just pretend that those aren't even on the ballot. Well, now the twist would be, well, president, I guess you have 5 choices. And vice president, you have 4 choices. So 5 times 4 would be 20. Yesterday I showed you another way that we could possibly write this. So is everyone good though that it would be 5 times 4 for 20? Okay. Here's another way we could write this. It's 5 factorial divided by 3 factorial. The rationale behind that was this is really 5 times 4 times 3 times 2 times 1. But 3 people didn't make the cut. I like the analogy of trying out for a team. You got 5 people trying out for a team, there's only 2 spots. So only 2 spots, 5 people, 3 get cut. Does that make sense? These 3 right here are the 3 who don't make the cut. And if I were to write it out like this, hopefully you can kind of see that this 3 would cancel that 3, and this 2 would cancel that 2, and that 1 will cancel that 1. It's probably fair to say that I don't think this notation saves you a lot of time because it's only like 5 times 4. But let's say we extrapolated the scenario and said, say there's 100 kids in the school and 70 of them get a free prize. So one more time. There's 100 kids in the school and 70 of them get a free prize. That's going to take a long time to write out, isn't it? Because you're going to have to go 100 times 99 times 98 times 97. What number are you going to stop at? Anybody know? If 70 of them get a prize? What's the last number I'm going to write? 31, actually. Because the reasoning is that if 70 kids get a prize out of 100, then how many kids don't get a prize? of 30.
30. Yeah, you wrote down 30, but it's like
Well, the reason why we're stopping at 31 is that 30 kids don't get a prize. And those are going to be the ones right here that are going to get canceled. Does that make sense? So in that scenario where there's 100 kids, 70 of them get a prize, a faster way of writing that would be this: 100 factorial divided by 30 factorial. The 100, how many kids are there total? The 30, how many don't make the team? Does that make sense? Or in this scenario here, how many kids were running for the ballot? 5 kids are running for the ballot. How many kids don't win? 3 of them don't win. Does that make sense? This scenario here that I just showed you is such a common scenario that it's been assigned a name. It's called a permutation. There's actually a shortcut notation for this on your calculator that I'm going to show you in a few minutes. So, but let me keep going through these examples. There's 15 kids at a birthday party. And we're going to give out a door prize of a stuffed animal, a gift certificate, and a DVD. How many ways can you do this? So again, think of this as like some kids win, some kids don't. So how many kids are there total? Oh, there's 15 kids, right? How many kids win? How many kids don't win then? That's the answer. But if you want to kind of write this out a little bit differently, maybe you could say it like this. This really means 15 times 14 times 13 times 12 times 11 times 10. I'm not going to write it all. And then the 12 factorial means 12 times 10, no, 11 times 10. See how like all that stuff's going to cancel? At its core, what you really have are, for the stuffed animal, 15 kids could win the stuffed animal. And then there's a gift certificate. 14 kids could win the gift certificate. And then there's a DVD. And 13 kids could win a DVD. And what happens to the last 12?
Yeah, we get nothing.
Nothing. Right. And like, aren't there everyday life scenarios that kind of fit like that? Think of when you go to Subway. When you go to Subway and you choose vegetables, in a way, you choose you choose 3 vegetables for your sub. I get lettuce, I get banana peppers, and I get cucumbers. In a way, I'm choosing 3 of them, and the remaining ones don't make the cut. Isn't that kind of the same sort of scenario? Sports teams, 15 kids try out for a basketball team, 7 get cut. Does that make sense? Either way, the answer is 15 times 14 times 13. I got 2730. Here's a tree diagram that kind of maybe illustrates the different possibilities. What you could do is you can kind of rearrange some different letters. Like let's say you've got A, B, and C. You could go A, B, and C. Or you could go A, C, and B. A, B, C, A, B, A, C, C, A, B, C, B, A. Like these are kind of just all the orientations that you could have. Does that make sense? I'm kind of writing out all of the possibilities. Here's another diagram. This is one I found that's just describing the way that you could sit on chairs. Let's say there were 2 of you, and 2 people needed to sit on 3 chairs. So here's a possibility. Abby and Ben. Abby and Beatrice could sit on the first 2 chairs. Or Abby and Beatrice could like skip the middle chair. Or Abby and Beatrice could skip the first chair. Or it could go Beatrice then Abby, skip a chair. Or it could be, you guys see how this kind of illustrates all the possibilities? Another way of approaching this would be, there are 3 chairs. How many chairs don't make the cut? Okay, well, 3 factorial is really 3 times 2 times 1. 1 factorial is just 1. So I'm going to write this out. There are 3 chairs. How many chairs do not make the cut? 1 chair. Isn't 3 times 2 just equal to 6? And haven't I just shown you 6 possibilities? So hopefully you get the concept, though, that this notation will be helpful if we have larger problems. If we're only doing 2 or 3 or 4 chairs, that's one thing. But what if there's 100 chairs and 80 of them need to get used? Well, if there's 100 chairs, 80 of them get used, that means 20 of them don't get used. So it's 100 over 20. I just put the picture on here of the marble slab because I like that analogy of like either going to Subway or, you guys have done marble slab before? Right, where you go there and they ask you, okay, well, there's 17 toppings and you get to have 3 of them. Right? In a way, that means that there are 3 that you're choosing and 14 that you're not choosing. All right, moving on. Let's try another example. Phil wants to buy 6 songs off iTunes. He's narrowed his choices down to 10. How many ways can he buy 6 songs out of the 10 he's choosing? Well, short notation then would be to say, well, there's 10 songs total. But it's not about how many songs he's choosing, it's about how many songs he's not choosing. So it's 10 times 9 times 8 times 7 times 6 times 5, basically. Because the 4, 3, 2, 1 gets skipped. Mm. 10 times 9 times 8 times 7 times 6 times 5. I got 151, 200. Have I made my point well enough that you guys can get the concept here? Okay. So let's skip ahead. Here it is. Okay. So this sort of scenario comes up so often that there's actually a button on your calculator designed to do this math for you so that you can just type it right in. Okay, now, so far I've been telling you that the fast way of doing it is to go total number, divide by the ones that don't make the cut. Your calculator actually has a function pre-programmed in called a permutation, but rather than being the ones who don't make the cut, it actually reverts back to the ones who do make the cut. Okay? And the way it works is you put in a number, n, first, then you use the symbol NPR, and then the last one, R. R is the ones that actually get to be chosen. Let me show you how to use this. So let's go back to this example here. Grab your calculator. So I already know the answer should be 151, 200. First type in 10, because there's 10 songs. Then we have to find the NPR button, and it's found under Math. Go way over to Probability, because that's what we're doing, and there's NPR. But then you have to actually type in how many of them you are choosing. Not how many you're not choosing, but this function is how many you do want. So in this case, we want 6 of them. So treat it as though there's 10 songs, you want 6 of them. And ta-da, there's the answer, lickety-split. Isn't that cool? Pretty much. So it's such a common scenario that there's a button pre-programmed in there for it. Technically what's happening here is you're doing n on the top, and then n minus r, how do I put this here? If r is the objects you are choosing, n minus r would be the objects then that you're not choosing. So that one more time. If we're going to define this r right here as the ones who do make the team, what your calculator does for you is it converts the bottom of the fraction into the ones that don't make the team. So it actually does that little conversion for you. So like if I told you there's 10 people, 6 of them do make the team, I think in your head you guys already did. Okay, well 10 minus 6 means 4 don't make it. Okay, that's what the calculator does right here. It just does 10 minus 6 to get 4. So let's try some more examples. Oh, actually, before that, I just threw on a slide just to remind me to talk about the implications when it comes to security. I think we've already talked about this a bit. Cryptography. I used that word yesterday, right? It's like the field of trying to make something really secure. The more passwords possible, the more secure it would be. If I wanted to hack into your cell phone and you had a 2-digit password on your cell phone, I bet you I could hack your cell phone pretty quickly. I'd go 00. 01, 02, 03, 04, right? Like eventually I'd crack your password, right? But if you had a 19-digit password, okay, granted that would be a little extreme for your cell phone, but do you really think I'd hack your cell phone password if you had 19 digits? It'd take a long time.
I think it was really long.
Why do you think your bank card has so many digits on it then? right?
So they can't crash.
Exactly, right? The more, the secure, right? So. Okay, let's do some more examples. Honestly, that's a lot of what this unit is I'm just going to do lots of examples. So here's a scenario. Let's say that you're playing like Scrabble again, and you have the letters G, R, A, P, H, I, T, E. You have a whole bunch of letters available. How many different three-letter arrangements can you make if you can only use a letter once? Well, the fast way of treating this is there's some letters that make the cut because you're going to use them, and there's some letters that you're not going to use. So how many letters are there total? 8. How many letters do you want? 3. Whatever that is, that's the answer. There are 8 letters. Sometimes I use the word pick. So like I might call this 8 pick 3. There's 8 letters. You want to pick 3 of them to use. What'd you get as a number?
336.
336? 336 then is the same thing as saying there's 8 choices for the first letter. There are 7 choices for the next letter. And there's 6 choices for the next letter. Right? 5 letters don't make the cut. Let's try another one here. South Africa, the way they make their license plates, first you have 2 different letters. Keyword, you ready? First you have 2 different letters. And then you have 4 different digits. So I was very emphatic on that. Because you have to have letters and numbers on the license plate. You can't have letters or numbers on a license plate. So, but it actually says they have to be different letters. So you can't use like AA or 5556 as a license plate number. So how many letters are in the alphabet?
26.
And you need to pick 2 of them. I don't care which 2, but there's 26 letters and you want 2 of them. How many digits are there?
6.
Sorry, you're ahead of me. How many digits are there? No, there's 10. But again, you can't repeat them. So, actually, you know what? This one, I gotta be really careful with the reading here, though. It actually said once a letter is used, it cannot be reused. It said nothing about digits. So if a digit can be reused, it means you have 10 times 10 times 10 times 10. So if I want to express this then using NPR notation, I would have to call this 26 pick 2 for the letters times by 10,000. Make sure you read really carefully because it didn't say that the letters or the numbers couldn't be reused. It just said the letters can't be reused. Does that make sense? Like that's where the twists are.
There's 6 million choices.
Which kind of makes sense because you probably want to have at least 6 million different license plates for all the cars there. Well, then they start doing things like in Alberta, it used to be like 3 letters, 3 numbers. And then they started doing things like 3 and 4, or 2 and 4, or 4 and 2, or you know what I mean? Like they just open up new combination possibilities. So, how am I doing so far? You guys okay with this? No? Let's try another example. 11 soccer players, and we want all 11 soccer players in a photo. Well, I guess you could say there's 11 soccer players, and we're going to pick all 11. Whatever that is.
Oh, that's a big number.
Yeah. Can I show you another way you could write this, though? You could treat it the first way I taught you, where there's 11 soccer players. How many soccer players are not getting chosen for the photo? 0, right? Does that make sense? And if you've got 11 people and you're choosing all 11, 0 of them are not getting chosen. The reason I want to point this out, though, is that normally you might look at a question and say, hang on, you can't divide by 0. Right? Like that's like the fundamental thing we taught you last unit. But 0 factorial is just 1. So it is actually possible to create a scenario then where 0 people are not being chosen. Okay, next example. Am I going too fast or is this okay? You're looking at me bored, but you've done this before.
Yeah.
How about everybody else? Is this
That's
okay?
Yeah, I'm glad there's that recovery.
Yeah. Like I said, I'm going to rip through like 4 times as many examples as I did in the last unit, but you get why, right? Like they're shorter. So. Do you guys have your SIN numbers? Do you know what they are?
Yeah.
I know my
You don't know your social insurance number?
So like your SIN number basically is you need it for like your taxes. Basically, it's your identification number for working.
Top ticket.
Yeah, sure. So here my question is, if there are no restrictions on the digit selections, how many different SINs can be created? Good. Devin's a little ahead of me here. Maybe the common thought would be, well, there's 10 digits possible, and we're going to pick 9 of them. But that's not right.
So it's 10.
Because it's actually 10 to the power of 9. Because if you start with a 3, well, you can use the 3 again, can't you? Is there no restriction? So I need to make sure you're really careful with the reading, because sometimes you can reuse a number, but sometimes you can't reuse a number. This whole permutation thing only works if once something has been used, you can't use it again. Does that make sense? Like if I ask you to take a card out of a deck of cards, once you have the card out of the deck of cards, it's been used. You can't use it again, right? But for like a digit on a SIN number, my SIN happens to have 2 3s in it. That's fine. Does that make sense? So you have to be really careful with the you have to be really careful with the context of the question. That makes sense? Okay, I just want to show you guys the notation that you might see. We didn't do this in 30-1, so this is a little bit new. Sometimes you might see it written as NAUNB. Here's what that means. This is the number of ways that A can happen, or the number of ways that B can happen. Does that make sense? If I wrote this, NA, with this symbol, that's how many ways A can happen and B has to happen. Okay? So 1 means that you're actually doing 2 things. Here you need to find a 7, and then you need to draw a 9. Whereas here means you could draw a 7 or a 9. So let's try this example here. A pin for a bank card can either be 4, 5, keyword here, or 6-digit long. How many pins are possible? So first one, let's say there's no restrictions. Well, in a way you have to deal with like some cases here. First you have to say, well, what if it's 4 digits? How many ways could you make a 4-digit password? Well, I'd say there's 10 numbers. And then, well, there's no restrictions. So then 10 times 10 times 10 times 10. That's how many ways we could do a 4-digit password. Or you could do a 5-digit password, which would be 10 times 10 times 10 times 10 times 10.
So can you do like NAU,
Yeah, that's basically what's happening here. Is this is the number of ways of having a 4-digit password, or the number of ways of doing a 5-digit password, or you can even do the next one. So then I've also got to add the 6-digit password to it, which is 10 to the 6. Does that make sense? So to add it together, I have to add 10,000 plus 100,000 plus 1,000,000.
111
4 zeros? Okay. Did that make sense to everybody? That question's a bit more complicated than the first ones we started with then, because we had to do some timesing and we had to do some adding as well. So that's where the twist comes in, is if you ever see things like or, that maybe kind of twists the question a bit. For the next one here, I say, well, what if you can't reuse a number? Well, okay, so then you can still do a 4-digit password. Now, maybe we can speed this up a little bit here. A 4-digit password where you can't reuse a number is like this. There's 10 digits, and you're going to pick 4 that you can use. That make sense? Because by picking a number, once you've picked it, you can't pick it again. Or you could do the 5-digit password, which would be 10 numbers and pick 5 of them. Or for the 6-digit password, 10 numbers and pick 6 of them. But again, we need to add them all together. So in your calculator, find what 10 pick 4 is, find what 10 pick 5 is, find what 10 pick 6 is, and sum them all up.
No, I have to find out. So I just gave up.
I got a 186 480. The two. If you can't reuse a number, wouldn't that limit the number of passwords? And so hopefully you'd see here that here there's over 1 million passwords. Here there's only like 100,000 passwords. So like if you can't reuse numbers, it actually really weakens the strength of your password. Make sense though? Okay, I need to fast forward again, just another twist here. So can I fast forward to, can you guys find this slide here? The one with the game, the 4 pictures, 1 word game? This was so popular a few years ago that it was, I put it all into my notes and then I don't know, you guys don't play this anymore, right? Like it's, you guys did play this at some point though, right? Okay, so let's try this example then. How many different words could you make? I mean, obviously we know that this is jump, right? But how many different possible words could you try to make? Well, you could go with J-U-M-P. You could go with J-U-M-B, even though it's not right. You could go with J-U-M-I, J-U-M-H, J-U-M-F, J-U-M... Hang on. Didn't I already count B? We have a name for this. It's called mutually exclusive. We actually cannot count it a second time because we already counted it, right? I can go J-U-M-S, J-U-M-K, J-U-M-V. But the real key I want behind this question here is that we sometimes have repeated letters, like the same item more than once. And that's a twist that I need to prepare you for, the idea of what happens if something happens more than one time. So one of the ways you could do that is then just say that there's a 1, 2, 3, 4, 5, 6, 7, 8 letters. So I guess there's 8 different ways you could do that. Or maybe you could just say there's 8 letters and I need to pick one of them. Does that make sense? 8 pick one, by the way, is 8, right? Doesn't that kind of even make sense? If there's 8 things and I ask you to pick one of them, there's 8. Or on this one right here, clearly that's the word water, I hope, right? But in terms of possibilities, you could do whatep, whatez, wati, whatef. But like, okay, well the Z's already been counted. R is the right answer. P's already been counted.
What have?
So even though there's 1, 2, 3, 4, 5, 6, 7, 8 different possibilities listed here, hopefully you'd agree that there's actually only 6 pick one possibilities. There's only 6 ways that you can answer this word because I can't count the P more than once. Or the Z, right? Does that make sense? Ouch. Okay, let me try another example that's similar to this. Let's say that your mom asks you to put away your dishes.
All the time.
All the time. Good. Chores are good for you. Okay. And you want to you're having fun. You want to arrange all the dishes into a fun little pile here. And it just so happens that there's 4 different colored dishes, but 3 white ones. Now, hypothetically, let's say that you took the blue and the yellow one and you flip them around. Would that be a different order? I'd say, sure, why not? But hypothetically, let's say that you took these 2 white dishes and flipped those around.
It doesn't really matter.
Yeah, isn't that the thing? Like, would it really matter?
No.
And that's kind of similar to the question I just did there, where let's say on this word here, you had to drag a letter into the spot. If you dragged this R into the spot, or if you dragged this R into the spot, would it really matter which one you used? I'd say, well, no, it wouldn't, right? Because they both get you the same thing at the end of the day. If you were to like rearrange some of these plates right here, you wouldn't actually see a difference. And so we need to have a way to like solve this problem of what happens if you accidentally count an arrangement more than once. That mutually exclusive concept of don't accidentally count something twice. So there's a formula a few slides ahead. Maybe I'll show you the formula a few slides ahead and then come back. When I originally showed you guys this concept of a factorial, I actually lied a little bit, a little white lie, because we weren't ready for it yet. But let's say that there were like 9 factorial things. If all of the different objects were different, what you would actually then do is divide by 1 factorial, 1 factorial, 1 factorial, 1 factorial, because each object was unique. However, if you ever come across a scenario where there's 2 letter P's or there's 3 white dishes, what you need to do is divide by 3 white dishes or by 2 letter P's. Does that make sense? And that's what this formula kind of refers to, is that the same of one kind. Let me go back now and do the previous example here. How many dishes are there total? How many? 7, right? So in a way, what you could do is you could say that there's 7 dishes. And we're going to do 7 factorial because we're going to use them all. However, there are 3 white dishes, 1 red dish, 1 green dish, 1 yellow dish, and 1 blue dish. Now, normally we don't write all these ones, because to be honest, you actually have been doing that all along. Every example I've given you up till now, we've always had unique items. But if you ever have like a repeated item or an identical item, you have to divide by that identical item so that you don't accidentally count too many options. Does that make sense? That's the key here, is that so that we don't accidentally count something twice. Anything that gets counted more than once, we divide by. So you probably don't need to write all those ones, but you do need to figure out in your calculator what 7 factorial divided by 3 factorial is, though. I got 840.
That's what I said, 800.
Oh, I thought you said 340. Sorry.
I got 840.
You got 840 as well? Does that make sense? So this is like a big twist, and this twist comes up a lot, okay? So it's the identical objects twist. If you ever have a repeated letter, the same dish listed more than once, sorry.
Take your time.
No, it's not my wife, so I'm not answering it. Okay.
Goals.
Does that make sense, though? If you have the same identical object more than once, that's the time where you divide. So let's try another example here, because I've only got 15 minutes.
Really?
Yeah, it's 1 something or
Oh,
different.
yeah, it's Friday.
I know, right? So, no, you get to go soon.
Woo, weekend.
Okay, do you guys see how in the word puppy, if we want to rearrange letters in the word puppy, the P is listed 3 times, right? So if you're going to use all of the letters in the word puppy, that's 5 factorial. 5 times 4 times 3 times 2 times 1. But hypothetically, let's say that you change the order of those 2 P's right there. Would it make you a new word? No, I mean, it would still be P-U, P-P-Y. It's just 2 different P's in a different spot. So the twist here then is we have to divide by the fact that there are 3 letter P's. Stay with me if you can, okay? If you wanted to, you could also divide by the 1 letter U and the 1 letter Y, but really that's not really useful. So,
I got 20.
20?
Yeah.
Does that make sense? Okay, let's try another example then, now that we've talked about this. How many different arrangements could you make using all of the letters out of the word scissors? Okay, well, if you have to use all the letters, that's 1, 2, 3, 4, 5, 6, 7, 8 letters. But hopefully you'll see here that there's repeated letters. If you changed around some of the S's, it wouldn't change the word. So we got to divide by 4 factorial. Any other repeated letters?
Oh, man.
No, I don't think so. So we just need whatever 8 factorial or 4 factorial is. 1680? It's not a bad unit, eh? It's short.
I like the other one better still.
Yeah.
I like algebra way better than this.
Algebra is very formulaic, where like you kind of do the same steps over and over again. These ones, they're all going to be very unique. Like they all have similar concepts behind them, but like every question is different. How many letters are in Mississippi?
11.
Okay. But then we got to figure out how many repeats there are.
4, 4, 2.
Yeah, 4, 4, and 2. There's 4 S's. There's 4 I's, and there's 2 P's. Okay. Now, if I can give some advice about how to put this in your calculator, type it like this. 11 factorial divided by bracket. 4 factorial, 4 factorial, 2 factorial, close bracket. Because you don't want to screw up the brackets whenever you divide by something like that. Put the whole bottom in a big bracket.
7, holy cow.
Yeah.
7983360. I didn't know.
Anybody else get that?
Wait,
I
I
don't
don't
know.
know.
Let me do
7,
that
33600. That's what I got.
Divide by bracket 4.
Is it supposed to be one big bracket or like?
Like I would go one bracket right here.
Like singular bracket. Okay, so I make it different.
Like did you do a bracket here and then a bracket here and then a bracket there?
Yeah.
Okay, then yeah, then yours is wrong then.
Oh,
I was like,
Okay.
Lisa.
No, okay, so 11 factorial divided by one big bracket.
brackets. 34. Yeah.
What'd you get?
34,650.
4, 6.
650?
No.
Oh,
zero.
no zero there.
6.
34650.
Yes.
Anybody else get that one?
Shoot, I did.
Okay, minus Lisa. You did the bracket in the wrong spot.
Yeah.
Oh.
Alright.
Alright. Makes sense so far? Okay, how much do I have left then? Okay, we're almost done. Okay, 2 more examples. Yeah, I'm sorry.
Actually, I like this.
We're actually not going to do the counting corners method, though. We're just going to do the left-right method. Okay. Okay, so here's another one here. Let's say that you have the word Canada that we need to try to figure out. But they're going to throw an extra twist on here. They're saying arrange the words Canada, but the first letter must be N and the last letter must be C. Okay, well that means then that you have 4 choices here and 3 choices here and 2 choices here and 1 choice here. So I can still throw on like a restriction that forces the first and last letter to be in a certain spot, but I still have to divide by the repeat letters possibility, because what letter is repeated? 3 times. So it's not actually 6 factorial over 3 factorial because they put a stipulation on. It's actually 1 times 1 times, like, I guess really this middle section is like a 4 factorial.
So there's only 4 ways.
Yeah. Let's try writing them out even. Just if there's only 4 ways, we should be able to write them out. So start with like an N and end with a C. We should be able to do like say A-D. Probably A-A-D-A. A-D-A-A. See how I'm kind of doing this like in a pattern here? And then start with D-A-A-A. Yeah, there's the 4 ways. If I flip those A's around, no one's going to notice the difference.
I almost did that as I was writing. This one thing I hated so much.
Still good?
See.
Okay, one last example. This one here we do in 30-1, but we're just gonna do the simple ones, Dakota. So you know the ones that might have like a grid like this, where then like this grid kind of carries off around the corner, or there's like a maybe a gap in the middle, perhaps. We're not gonna do those ones. So we're just doing them like this. Okay, so this is a very unique type of problem. Basically what it suggests is how many ways could you go from here to here? Like imagine that you're walking from your house to school or something. You could walk like all the way over and then walk down. Or you could walk all the way down and then over. Or you could go like a zigzaggy kind of pattern. Or maybe you could do like this sort of zigzaggy pattern. The restrictions, by the way, are that you can't like cut through a yard. Okay, that's an obvious restriction. There's one more restriction, is that you can't do something like this. Go over, come back again. Like that wouldn't be a valid pathway. Does that make sense? Like, so you can only go down and to the right. If you get a question like this, it actually involves the same principle. The principle would be that regardless of how you're going to walk, you're walking 7 blocks. Let me see if I can show you why. Let's say you go this way. you're going 1, 2, 3, 4, 5, 6, 7. Does that make sense? You're walking 7 blocks. Or if I use a new color here, say I go this way. I'm still going 1, 2, 3, 4, 5, 6, 7. Or a third color even. Let's say you go there, 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 which is to zigzag the thing. You're doing 1, 2, 3, 4, 5, 6, 7. Does that kind of make sense that regardless of how you do this, you have to walk 7 blocks? Like there's not a shortcut in there. So you're definitely walking 7 blocks. However, some of the blocks that you're walking are kind of repeats of each other. In a way, you're going to be going right 4 times. I guarantee you, regardless of which way you go, you're going to be going right 4 different times. Or here, 4 different times you're going to be going right. And 3 different times you're going to be going down. Now, does it matter which order you do the rights and downs? Not really. So in a way, you could write it out like this. You could go right, 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 down, 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 down. Or you could do, no, sorry, I need 4 rights. Or you could do down, right, right, down, down, right, right. But you know what I mean? Like at the end of the day, you have the same thing repeated. You have 3 blocks, which you're going down, and 4 blocks in which you're going right. And it's kind of the same concept applied to a unique scenario here. So if you ever are given one of these questions, the easy way to solve it is to figure out how many total blocks you have to walk, but then divide by how many are to the left and how many are down, or how many to the right and down. Does that make sense? So for this one here, just again, make sure you put a bracket around the 3 and the 4. So.
It's 35.
35? Anybody else get that one? Cool. You did like the 1, 2s method? Yeah, we do that with Dash 1 kids because we talk about Pascal's triangle. And
That was my first instinct
yeah.
to do it that
Wait,
way.
guys, give me 1 minute here just to summarize. Maybe even just listen while you pack. So, all we're doing now is just adding more twists and tricks. Okay, little restrictions. Things like, what if the C and the D have to be first and last? Or what if Brad and Angelina have to sit next to each other? Or what if Brad and Angelina can't sit next to each other?
Good volume students, please come down to the office at the bell. Liam Scott Worthing,
Today's
Eric
restriction,
Yellowhorn, and Roy Fournier.
Today's
Please come to the
restriction
office at the
is
bell.
that what if the same thing is in there twice? What if you have 2 letter Ds? What if you have 3 plates that be the exact same? Okay. So I'm showing you basically some shorthand notation. That's basically the concept. Okay, last thing here. I'm not here Monday, Tuesday. Okay, I'm going to print off an assignment for you guys to kind of work on for those 2 days. Can you guys also grab your booklets back and work on some practice questions in the duotangs as well? And then Wednesday we'll debrief and see how far you guys got. Does that work?
Put your
Wait,
chairs
cool.
up.
Oh yeah, by the way, can you put your chairs up?
I brought this.
Can I do my math unit test on Monday?
Yeah, there's just a copy of the test folder, so just grab it out of there when you're ready.